All right, good evening. My name is Matthew Petting. I'm team lead of Light Aircraft Solar Extended Range, or LASER.
My name is Jan.
I'm Yen-Chen Liu.
Matt Gustafson.
Austin Gerber.
Zach Cooper.
Hugh Schuster.
Logan
All right, in laser, our objectives are mainly to design, build, and test a solar-powered remote control UAV that is capable of long-range flight. With that, we want to pursue the world record of longest flight in a straight line by under FAI regulations of the F5 SOL category. The world record, I'm pretty confident to say that the world record is 46 kilometers, which is around 30 miles, set in 1997. And we also would like to extend the range and endurance of the aircraft using solar energy and hydrogen fuel cells. The impact of our research provides not only insights to aviation, it also provides significant implications on other fields such as innovative airframe designs, control systems, power systems, and management theories. It also shows the applications of scientific development in real-life situations and demonstrates the practicality of using alternate energy on aircrafts. Our limitations when it comes to manufacturing and design for under the category we're in, which is the F5SOL category, we have to use an electric motor propulsion. We must have a radio-controlled flight without the use of autopilot. The maximum surface shadow area must be 1.5 meters squared with a maximum mass of 5 kilograms. And the only power source we can use is for propulsion are solar cells.
This is our current model, Laser 5. We start building this from last semester and it's getting to the final point of construction this semester. And here's the preview of our model. The total wingspan is 14 feet and it's a 2-piece wing, and we mount it together at the middle and sitting on the top of the fuselage. The fuselage has the same geometry as a prototype, but with the smaller diameter and the longer length. For the tail, we decided to use a conventional tail instead of a T-tail, which will give us better controls and easier to manufacture.
Our fuselage is a 1/4 inch of foam with a carbon fiber sleeve wrapped around it. The way we made that was we had 2 halves of the fuselage CNC'd. We then hollowed those out, glued those together, and then put the sleeve over it and hung it from the ceiling. Then applied the epoxy and used the heat shrink to ensure a tight fit and also get rid of the excess epoxy. The wings are ribs and spar designs with 2 spars and a bunch of 8 ribs that are all made out of carbon fiber with a monocoat skin, and we had to add 1/16 inch balsa wood to support the skin in between the ribs to avoid sagging. We attached that by making a middle wing section, which we attached to the fuselage, which has a ferrule in it, which we then slide the wings into the ferrule and secure it by sliding a pin through the ferrule and the forward spar.
Here you can see an analysis we did last semester in XFLR 5. Our wing, because of its high aspect ratio, gave us very small wingtip vortices. It also had a very nice elliptic lift distribution. This semester we did another analysis more thoroughly with the entire plane. You can see it right there. We got lower L/Ds. We also tested an X-plane, and in the X-plane we saw we had an L/D of about 32. We also found out that it handles very well, but it is a bit pitch and yaw sensitive.
Okay, with all that being said, Laser 5 is practically complete. It's been built. We just have small tweaks. So we started design on Laser 6. Laser 6 is going to be a flying boat. We decided to do that. The importance of choosing a flying boat gives our EEs time to implement the solar panels on Laser 5 and then use that on Laser 6. It allows us to experiment with different manufacturing practices and techniques. And then it allows us to build an up-to-date trainer as a testbed aircraft for electronics. Some of the reasons why we chose a flying boat, you can land on the water, charge your battery with the solar panels, and take off again. Gives you more places to land, which would be nice. It's a difficult challenge, but it's exciting. And then possible implementation with hydrogen fuel cells. Some of the key differences of a flying boat is the fuselage design. We will be landing on our belly, so the fuselage will act as kind of like the landing gear on the water. The propeller location, it'll have to be above, so it doesn't interfere with the water. A water rudder to steer while we're in the water. Wing floats, so we don't sink when we have a high wind gust in the water. T-tail design, waterproofing to keep our electronics safe, pretty important. And some buoyancy calculations so that we make sure the boat stays afloat while in water. Some of our performance goals for Laser 6, take off and land in calm water, make some amphibious landings, so water and land, just land on the belly again. Maintain waterproofing so that our electronics stay safe. It's very important, especially with hydrogen or with the solar panels. Implement the solar panels on the airplane eventually. This will again allow for us to land on the water, allow our battery to charge with the solar panels, and then we take off again. Low cruise speed and gentle stall characteristics. This will allow for us to gently land on the water so we don't do any damage to the fuselage or to the plane in general. And then also we want to make it easy to manufacture and repair in the case that we had to have a rough landing or some kind of destruction of some sort. This right here is our overview of Laser 6. It's preliminary design, nothing set in stone, but this is kind of what we have so far. Again, the wing, the fuselage, the T-tail, and then the propulsion mounting system, a little bit different than we've done in the past, but all these will be explained here in a few.
So the first step in designing the wing is to determine an airfoil. We decided to go with the FX 63-137. A few reasons for this. First of all, it has a high CL receding max that occurs at a low angle of attack. Basically, that means it'll have good gliding characteristics. It also has a very high CL max, which means that we'll be able to have a low cruise velocity. It also has very gentle stall characteristics, which kind of decreases the likelihood that you'll lose control of the plane. And the only major downside of this airfoil is that it has a high moment coefficient, which means the airfoil will induce a nose-down pitching moment. For the wing, we decided to go with a rectangular plan form. We decided to do this because it'll be very easy to manufacture because it has a constant chord. It also has good stall characteristics. As you can see from the figure, you're very unlikely to have tip stalling. And it'll also be easy to implement the ailerons because you have a nice straight trailing edge. Now the cons of this plane form are that it does not have an elliptic lift distribution, so your wing won't be as efficient, and it'll have a strong tip vortices, which means that our induced drag will be a little bit higher. The key dimensions are that it'll have a 10-foot wingspan, a chord of 14.5 inches, and that'll give us an aspect ratio of 8.27. We did some star CCM CFD analysis on the wing, and we found that at 20 miles an hour with an angle of attack of 10 degrees, our wing will produce about 15 pounds of lift, which means we'll have a very low stall speed. This is our fuselage design. We're confident in this design because it's based off of a NACA design that's been proven. A few distinguishing features: that it has the step right in the middle. That allows the plane to sit on two surfaces when it's on the water, and that reduces your skipping when you're at speed. It also has spray strips to control the flow of the water when you're at speed. Basically, it prevents the spray from getting on the wings and propeller. And it also has a large hull, which means plenty of buoyancy and lots of internal space for your electronics. For the tail, we, as mentioned, decided to do a T-tail. We did this because it's aerodynamically efficient and it keeps the horizontal stabilizer high above the water. And it'll also be very easy to implement a water rudder. To size the tail, we used a computer program to analytically determine the dimensions so that we could optimize. We have a large horizontal stabilizer, and that allows us to have more stability.
For Laser 5, we used the carbon fiber ribbon spars, and that provided us a very lightweight and stiff wing structure, but unfortunately carbon fiber is not overly cheap. So we were looking into shifting to a composite shell structure with a fiberglass skin with foam ribs, and the fiberglass would actually be the load-bearing structure. In this photo, you can see a bunch of different samples that we made with different weights of fiberglass. Unfortunately, we discovered that that is quite dense and would cause our wings to be too heavy. So we are shifting to experiment with foam core composite beams, which are more economical and efficient than solid spars. With the fuselage structure, once again, we're going with a precision CNC machined extruded polystyrene core with strategically positioned fiber reinforcement. And we're going to, our goal is to experiment with various fiberglass and carbon fiber reinforcement to make the plane lightweight, but also durable enough for these belly landings.
These are the 3 boards we'll be using for laser. The one in the top right corner is our solar power converter, which takes the unstable energy that the solar panels produce and converts it into stable, usable energy for our plane. The far center, the left center one, is our battery protection board, and it monitors the behavior of the battery by checking the currents, voltages, and temperature to make sure nothing irregular happens, so we know everything's running smoothly. And our last board in the far right corner is our Autopilot and our newest, and it helps us simplify telemetry, and it's a programmable board.
So far in the year, we have researched for Laser 6, deciding whether to go with 1 motor over 2 motors, whether to change up our battery to work with a more friendly battery, and we've also looked into changing our solar panel array. A lot of this year so far has been getting caught up with what has happened in previous years of Laser's electrical engineering. And right now we've just started working with the Autopilot, which is very nice with its telemetry, and it also is what ties the other boards together and actually makes them function correctly.
Some goals we have for the semester are to implement the Autopilot. The advantages of that are, as we mentioned before, we're looking at replacing the current solar panels with more efficient panels. Better panels would mean larger distance for us, which is a big advantage, and discovering new effective options to replace the Autopilot. The Autopilot requires 5 volts to operate, and an optimal for our battery would be 3. So we're currently weighing the options to choose which one would be preferred.
And here's just a brief overview of what we plan to get done over this next academic year. There's lots of electrical research, work, and design being done over the course of both semesters. And we're designing Laser 6 in the first half of this semester. And the rest of this semester, as well as next semester, will be primarily the construction of Laser 6. So some of our future plans include the obvious goal of completing Laser 6, and as well as finishing Laser 5 and taking that on test flights. And if possible, take Laser 6 on some test flights as well. We'd also like to conduct more STAR CCM and ANSYS analysis, and also implement our solar panels successfully. We'd also explore our options with hydrogen fuel cells, and we'd like to continue our research with the electronic systems to make them more efficient and optimized. Here's a brief budget that we have come up with. We're not asking for too much, but we're asking for a sufficient amount to complete our goals. And it's not as much as we asked last year because we've become more efficient. So with all that being said, we'd like to thank Matt Nelson and Ambar Mitra, our advisor, as well as the M2I team and department, along with our sponsors, including PowerFilm, Boeing, Alliance Pipeline, Advanced Circuitry, and Rockwell Collins. So with that being said, thank you for your time, and are there any questions now?